Alright, welcome back. So the topic of today's lecture is prior specification. So how do we specify prior distributions on our parameter of interest? Okay. Now this topic is important because what would happen is that in most situations you would be in this uncertainty that what prior distribution should I choose for a certain parameter. Okay. And that's a valid concern when you are doing Bayesian modeling. Okay, so there is a whole sort of idea that how you should specify your prior. So basically, there is a theoretical basis that what is actually a prior distribution, and then when it comes to practice, then you will need to make some decisions that what kind of prior distribution could be reasonable one to make here, right? So what I will do in this lecture, I will describe all those 5-6 ways in which you can specify prior distribution on your parameter of interest, right? So there are 5-6 ways to do this. Okay, so depending on the situation and the context, you will need to specify your prior. Okay, so you can make your decision based on what situation you are in. Okay, so I will describe those situations and the decision you can take to specify your prior. Okay, so let me begin. So in Bayesian modeling, the idea of prior distribution is this, that you make some assumption about underlying generative process. So let's say in an experiment you observe data xi in ith trial. So you assume that xi comes from some underlying distribution, let's say f of x theta, where theta is the parameter of this generative process. Now in the Bayesian framework, you treat theta, all these parameters, as random variables. So that means theta would have its own true distribution. Okay, but we do not know what is the true distribution of theta, so we make some assumption. We assume that the true distribution of theta is p of theta. Okay, now we will see some data. So let's say you observe some data x1 to x10. So given this data, let's say x1 to xn. So given this data, you would make inference about true values of theta, right? So what could be the true distribution of theta? Okay, so true distribution of theta after seeing the data, right, conditional on this data, will be given by likelihood of theta given x1 to n into prior distribution of theta divided by marginal likelihood. So here the role of prior distribution becomes very important. So what is your prior assumption, prior belief about true values of theta before seeing any data? So after seeing the data, this will update and this will become like this. So your inference, so this is your inference about what are the true values of theta that might have generated your data. Okay, so this inference about theta is dependent on these three things: the likelihood assumption. What is your likelihood assumption? What is your data? It also depends on data, right? Let's say you collect, you run the same experiment again, you might get a different data. So it depends on the data as well. And third thing, it depends on your prior assumption. Your prior assumption about theta. Okay, so the role of prior assumptions is important because it directly contributes to your inference about theta. Okay, and idea people get about prior distributions is this: they think that we should have completely uninformative prior so that it does not affect our inference about the posterior, so that prior is not contributing to our inference about parameter theta, only data is contributing to our inference about the parameter theta, right? But in that case, if your prior is completely uninformative, then you are just getting back your likelihood function, right? Then there is no point in computing the posterior, right? So that's not the point of Bayesian inference. The point of Bayesian inference is this, that we can specify our prior assumptions and make inference under different set of prior assumptions. So we want to utilize this, right? This is a very powerful, flexible tool at our disposal, that under different prior assumptions about parameter theta, you end up getting different inferences, you end up getting different kind of predictions from the model, right? So one set of prior assumption is a model in itself. You can have another model with different set of prior assumptions. This is a very powerful tool, and I will show some real practical applications of specifying these prior distributions. For example, some of the things that you can never do in frequentist framework, you can do using exactly the same idea of prior assumptions. So, for example, in frequentist inference, you cannot quantify how much evidence do you have for your null hypothesis compared to an alternative hypothesis. Something like that you can implement in the Bayesian framework. You can compute evidence for a model which assumes that the value of parameter is 0 against a model which assumes the value of parameter is positive. You can do that, right? So, this allows you to do a lot of things. It allows you to flexibly test certain theoretical assumptions, right? So, we do not want to give away the flexibility it provides, right? And that's the whole point of Bayesian inference. It's central feature, right? So, what is the way out? We need to become sort of skilled at specifying prior assumptions, and it's not that difficult. Let me show you how. Okay. So, by definition, when we talk about prior distribution P of theta, you will see these terms written in certain textbooks or in papers, that this is prior assumption, or you would see this is prior belief about true values of theta, or you might see this is prior information about theta. Okay, so you might see these words and maybe a couple more, right? And they have slightly different meaning in different contexts. So, the idea is this, that sometimes what can happen is that let's say you are investigating a Stroop task. Let's say you're trying to model reaction times in a Stroop task, right? Now, you have done the same task before, you or some other researchers in the field. Historically, the Stroop task has been done multiple times. Okay, so you have huge lot of prior data on the same task, right? So, that means you already would have some information about the parameters in your model. So, let's say you make some model that reaction time on IF trial on a Stroop task comes from, let's say normal mu sigma. So, to specify prior on mu, you already know a lot. Mu is average reaction time. You already know about average reaction times that you observe in Stroop tasks, right? So, there is a history of a Stroop task. It has been done so many times, right? So, let's say you collect or you recall all that information from previous Stroop tasks, and based on all that information, you think that the average reaction time observed on Stroop tasks are somewhere between, let's say 300 and 350 milliseconds, right? So, you can specify a highly informative prior on the parameter mu. Okay. So, that is the case of prior information. You have prior information about theta and you can use it in your prior distribution, right? Also, if you are not very confident about these previous experiments, well, they have been done, but you are not very confident. Let's say they were low sample size studies, or the task they were doing had a lot of confounds and all that. So, you do not completely trust this information. So, you might want to add up some assumption or some belief in this. So, let's say you would say, well, I will use this information, but I would also allow some skepticism. So, I would say that likely value of mu lies somewhere between, let's say 250 and 400 milliseconds. So, then I will determine a prior accordingly, let's say normal 350, 50 something, right. So, you can do that. Now, in this case, you are using prior information as well as you are inserting your own assumptions or beliefs, okay, so that there is more uncertainty than this. So, this is the case of prior information. Now, let's say you are working with a task about which and on this task there is no prior studies that involve this task. Let's say there is a completely new task We are comparing two conditions A and B, and there is no prior studies involving this task, right? In that sort of situation, you might have very little information about your parameters of interest. Let's say mu, sigma, you have very little information about your parameters of interest. What would you do in this situation? Well, in this situation, you need to specify what you assume or what you believe about these parameters. So, you need to specify prior distribution using your assumptions or using your beliefs, right? I am saying these two terms separately. Let me show you why. So, in this sort of situations, there could be different ways to specify your prior distribution, right? One way is this, that you don't know anything about this experiment. No one in the field knows anything about this experiment. Okay, so this is completely new. No one has any opinion on this. In that case, you will make some reasonable assumptions. So make reasonable assumptions. Let's say the parameter is theta. You would make some reasonable assumption about the parameter theta. How do you ensure that your assumptions are reasonable? Using prior predictive checks. So, you can always do prior predictive checks to see if your assumptions are reasonable. So, generate prior predictive data from the model and see if this is the kind of data you would see in the experiment. Okay. So, specify some reasonable assumptions if you do not know anything at all and no one knows anything at all, right. So, this is one situation. Another situation you can be in is this, that this particular task has been done before by a few other researchers, and people have different opinions and different beliefs about certain parameter, let's say effect size. Okay. In that situation, you can express your belief as well as opponent's belief, as well as some skeptic belief, as well as some highly confident researchers' belief. You can express their beliefs using prior distribution. So, let's say hypothetically, you assume about a parameter theta, or you believe about a parameter theta that its value, let's say it's about some effect size, okay, let's say parameter is beta. So, let's say its value lies somewhere between minus 20 and plus 20. This is your belief. Okay. So, let me call it your belief. Okay. There is a researcher in the field who is very confident, let's say your opponent, who says that beta is always positive, and the researcher also makes a claim about what is the likely value of theta. The researcher says the likely value of theta is somewhere between, it's a large effect size, and somewhere between, let's say 40 and 60 milliseconds. So, this researcher, opponent researcher, believes this, that the likely value of beta is somewhere between 40 and 60. Now, there is a skeptic in the field who says that, well, the effect of beta could be positive, but I do not think that the effect size is too large, right. The effect size has to be small. So, let's say this researcher says that beta is positive, but I don't know how big is the effect size. So, let's say it's normal 0, 20 or something. So, it allows effects beta to be between 0 and 40. Okay. And there could be someone else, opponent 2, who thinks completely opposite, says that beta is strictly negative and could be anywhere between 0 and 40. Okay. So, these are different beliefs about the parameter theta, which you can specify as prior distribution. So, this will make, let's say 4 models. Now, you have 4 models, right, of the underlying process with different prior distributions on beta. You can compare these 4 models to check which belief, which prior assumption is better at explaining the data, right. So, this is another way in which you can specify the prior. So, using beliefs, your belief, opponent belief, skeptic belief, right, you can use all those as prior distributions, right. So, just to summarize, what are the different ways to specify prior distribution? First, use information from previous studies or previous observations on the same task. Okay, so for example, you can use even posterior distribution from previous study. Okay, as we use in Bayesian learning process. Okay, so this is, we are using information from previous studies on the same task. Second, you can do a much more systematic process to retrieve information from previous studies. What you can do is something called meta-analysis of previous studies, of all previous data, to infer a prior for theta. So you have data from all previous studies, and given that data, you estimate posterior distribution of your parameter of interest, okay, given all those studies using a hierarchical Bayesian model, and that posterior distribution now can be used as prior for your own study. So actually there is a way of doing this. You can do a meta-analysis of all previous studies. Okay, so maybe there are some previous studies which says that theta is somewhere between 20 and 30. Other study says that theta is somewhere between -10 and 0, and so on. Right. So studies would differ. So you can estimate a meta-analytic estimate of theta. So given all the data, what are the likely values of theta? It could be somewhere in middle, for example. Right. So that's meta-analysis estimate. What this meta-analysis estimate ensures is that you would rely on studies which are large sample size more compared to the studies which have lower sample size, right? So basically your inference about theta, your prior about theta, would be more informed by high powered studies. Okay, that is what you achieve here. So your estimate of theta or your prior distribution of theta will be more informed by high powered studies. So studies with larger sample size compared to low powered studies. Okay. This is way 2. This is when we have data from previous studies. But now we are in a situation, let's say, where you do not have data from previous studies, you do not have a lot of information about the parameter from previous studies, but there are researchers in the field who have done similar tasks, and they have some beliefs based on their theory or based on some empirical data. They have certain beliefs, right? So let's say there are different researchers in the field who believe something about the true value of the parameter. Okay, so you can call this specifying priors based on researchers' beliefs. So it could be your belief, skeptic belief, or some opponent researcher's belief, right? Some researcher committed to some theory one, so based on that, right? So it could be based on researchers' beliefs, right? So let's say some researcher believes that, let's say beta has to be, let's say somewhere between 10 and 30. Okay, so that's a researcher's belief, right? This is the third sort of way in which you can specify priors. Fourth, you can describe theoretical assumptions as priors. So sometimes you have well specified theories about certain task, certain experiment, or certain generative process. So you have theories, right? And theories might have to say something about likely values of a parameter. Okay, so let's say a theory says, that's a theory one says that beta has to be positive. In that case, you can specify positive prior on beta. So let's say the beta has to have a positive value, let's say between 10, 20. So anywhere between 0 and let's say 50. Okay, and likely values are around 10 or maybe 20. So that you can decide. Theory 2 says that the value of beta is negative. So let's say it has this prior. So you can describe theory 2 using this prior. And let's say theory 3 says that beta is 0. Okay, this is your theory 3. So now you have 3 set of prior assumptions based on 3 theories. So you can describe your prior distribution, prior assumptions based on theoretical assumptions, right? So if you have well specified theories that have to say something about the parameter of interest, right? When you don't have any of this, when you don't have any prior data to give you some information, when you don't have any other researchers having some opinions or beliefs about the parameter, when you don't have well specified theories about the task, right? Then in that situation, let's say it's a completely new task, then you are on your own. Then you still need to make some reasonable prior assumptions. Okay, so reasonable assumptions. So that's how you will specify a prior. So let's say you make a reasonable assumption that beta is, let's say, somewhere between minus 40 and plus 40. So in this situation, you can specify a weakly informative prior. A prior which is not completely uninformative, it is slightly informative but weakly informative. So it wouldn't affect your posterior too much, but it would still have some basically quantifiability about what is your assumption, right? So maybe it wouldn't affect your posterior much, but based on this prior, you can say that you had a prior assumption that the likely value of beta is between minus 40 and plus 40. Okay, why this is important? Because now you can test, you can compare it with some other assumption. So let's say, what would be your inference? How well the model would do if you assume that beta is somewhere between normal 0, 10. And that's a very useful kit to have, right? So basically, you can test the performance of your model under different prior assumptions you are making. Okay, and then you can say that, well, under these prior assumptions, model is doing good. Under these prior assumptions, model is doing bad, right? So that's why this becomes very important as well, right? So these are the 5 ways in which you can specify priors, right? So if you have information from previous studies, you can use that information as prior directly. If there are a lot of studies which have very different sample sizes, then you can do a proper systematic meta-analysis to get a more informed prior distribution, such that it's more informed by high-powered studies and less informed by low-powered studies. You can also use different researchers or opponents or skeptics' belief in the field, in the community, about certain parameter, and use all those as prior distributions of the parameter of interest. Then you can also use certain theories. You can basically retrieve from a theory that what this theory says about the values of this particular parameter, and then specify them. For example, let's say theory 1 says that beta is negative, theory 2 says beta is positive, theory 3 says beta is 0. Now these are 3 competing prior assumptions about the parameter beta. Then if you don't have any of this, if you do not have any information at all, any researcher, any theories about the phenomena of interest, then you can still specify reasonable assumptions. How do we make sure these are reasonable assumptions? Using prior predictive checks. We can check the prior predictions generated by the model. Do they make sense? Is that the kind of data you would expect in the experiment, right? So in this case, you will do prior predictive checks. So you can do prior predictive checks. Okay. What happens in practice is that we are often in this situation 5. So we have very little idea about the particular task, that what could be likely values of our parameter. So one way to go ahead in these situations is this, that you specify priors based on your experience, right? So for example, let's say you assume that the reaction times come from a normal distribution, then you will have parameter mu and sigma. What could be likely values of mu and sigma in a reaction time experiment? That would come from your experience of those previous studies, right? As well as the assumption, if you want to make some explicit assumption. So for example, I have done reaction time kind of studies a lot in the past. I personally have done them a lot. So I know that reaction times are typically in milliseconds, so somewhere between, let's say, 100 millisecond to 1000 to 2000 milliseconds. So they are in this range. So the average reaction time would be, let's say, somewhere around 300 to, let's say, 600 milliseconds, even less or more slightly here and there. So I can specify a prior accordingly, right? Similarly on sigma, that how much is the standard deviation of reaction time. So let's say it is around 50, 60, 70 in that range, right? So I know this from my prior experience on these studies on reaction times, right? So that's what I can use in practice, right? In the situation when you don't even have any prior experience, then it's very important to do prior predictive checks, so that just to ensure that you are not specifying completely weird priors. For example, that can happen. Let's say for the first time in your life, you are using log normal distribution. You are using log normal likelihood, right? So if you assume that reaction times come from a log normal distribution, it would have parameter mu and sigma, but their interpretation is now very different. They are on very different scale, right? Now in this situation, if you specify a prior on mu, which is somewhere around 300, then that is going to be very unreasonable prior, because now the model will generate reaction times in the range of 10,000 or 50,000 milliseconds, right? So because now mu here is somewhere around 5, 6, right? Because it's a log normal distribution. So mu is on log scale, right? So it becomes important to do a prior predictive check in this situation. Okay. So this is it. So these are 5, 6 ways in which you can specify prior distributions. So this is the skill you need to develop basically step by step, that how you can effectively use the idea of prior distributions in Bayesian modeling, and how you specify reasonable prior distributions for your parameters of interest. Right? All right. So, but most part of it you will get as we go ahead in this course. When you start doing actually regression modeling, then you will understand that what all these things mean and how we can use all these kind of information for eliciting priors. Okay. All right, I will stop here. Thank you very much.